Hey, good morning. Assalamualaikum. Today we will start chapter 3. Last class kita dah habis chapter 2. Later I review your exercise. Okay, just to recap, chapter 1 is the introduction part to fuel combustion, which you need to know how to do the fuel analysis, approximate, ultimate, everything. Identify your type of fuel. Okay, then find out your chemical formula for solid fuel. Okay, that one is chapter 1. Chapter 2 is about the combustion process, where you need to identify your fuel and the products. Can and then come up with your combustion equation. And then chapter 2 part 2 is about the combustion product analysis. Kan? Where you need to know the mole fraction of your products. Okay. Now, chapter 3 is about the heat of combustion. From the combustion process, per heat, how much the heat generated and what type of heat of generated. Okay. Okay, for the first law analysis, the main purpose of combustion is to produce heat. Produce heat through a change of enthalpy from the reactants to the product. Okay, reactant is your fuel and air. Then products, whatever products that you produce. Okay, by ignoring in controlled volume means no changes in the combustion chamber volume. Okay, by ignoring kinetic and potential energy, assuming no work done. So we have this Q of combustion equivalence to total enthalpy of product minus reactant. P stand for products, R stand for reactant. Okay, so ini dia punya main equation lah. Q produced from the combustion. Equivalent the product, heat produced by the product minus heat produced by the reactant. Okay, so from there we know what is the heat produced during the combustion. Okay, the N is the mole of each component. H is the enthalpy of each component. Okay. Now there are three components of heat in combustion. We have heat of reaction, heat of combustion, okay, heat combustion, sensible heat of the products, and latent heat of water evaporation. Latent heat. Okay, sensible heat, the difference is, as shown here, sensible heat bila the component being heated, temperature change, but the phase doesn't change. That is sensible. So heat produced along the process we call as sensible heat. Sensible, no changes in the phase. Okay, no phase change. Whereby if latent heat, we heat up the component, then it change the phase. So latent heat. Okay. Okay, usually for the STP, as I mentioned earlier, at STP, we always refer at 25 degrees C, 1 atm, and denote as this one. Because most of the time I pronounce as not. Okay. This is the common reference state to evaluate the enthalpy. STP, standard temperature pressure. Okay. Okay, the enthalpy of a chemical component at a specified state is the sum of the enthalpy of the component at 25 degrees C at standard state and the sensible heat of the component. Okay, so dari equation ni, enthalpy H. This one is the heat of formation. Heat of formation is dia punya original enthalpy to form that particular component. Okay, ini adalah sensible heat. Sensible heat, sorry, saya ulang sorry, not sensible heat, sorry. I repeat. All this is the sensible heat. Semua ni sensible heat. The heat produced from the process. Okay, the H plus ni adalah heat at specific temperature at T. H naught, this one is heat at STP. Okay, from ini, saya copy this figure. Okay, so for example, dalam figure ni, kita guna water kan. So, liquid. So, H enthalpy of the liquid, enthalpy of the water, equivalent to HF of the water, H2O. So, this one kita akan cari at table A26. Ini dah fix the figure. And then, plus the sensible heat. Sensible heat means the heat produced while the heating process. How much heat produced along the process kan? So that's why the T, H ni, is at specific T, at final T. So from here at 100 degrees C, for example, at 100 degrees C. Okay, minus H naught. H naught here is at STP. Naught refers to the STP. Okay, so tapi in this case, you are the the starting point of the temperature, which is not at STP kan. So this one can change to H at T1. This one is at T2. So case by case lah. If the statement mentioned the condition is at STP, the initial condition is at STP. So you use H naught. Kalau initial condition dia ada another temperature which is not at STP, so you should refer the H at that particular temperature. Okay, later we go for exercise. Okay, consider the following reaction taking place at atmospheric pressure. 298K equivalent to 25 degrees here. Okay, so dia punya ni, this one formation of water, H2O, in liquid form, where it involves reaction between O2 plus H2 and CO2, C plus O2. Okay. Okay, in this reaction, H2O and CO2 are formed from their elements in their natural state at standard temperature and pressure. Okay, 1 atm and 298K. Okay, this is called as formation reaction. So the HF, heat of formation, is coming from this reaction. The value generated for heat of formation of water, for example, datang from this reaction. Okay, Q is referred to as standard heat of formation. This one. Where we always refer in table A36. Symbol HF. Okay, so this one is standard. You can find from the table. No need to calculate. Okay, the sign over here. Do you understand the meaning of the sign? Kita ada negative and positive. Negative, what is it? Negative exo. Exo, negative. Maksudnya? Yes, release heat. Release heat. Endo, they absorb heat. Okay, note that the enthalpy formation of basic element, basic means the O2, H2, C is always 0 because they appear in their original state. So it is not formed from something else. Okay. Okay, this one similar to as what I explained earlier. This part is the sensible heat. This is the heat of formation. Okay. Now we move to the example. So far okay tak? Boleh faham new concept? Okay. A gas stream at 1 atm contain a mixture of CO, CO2, and 2, in which the CO is 0.1, CO2 0.2. Okay, the gas stream temperature is 1200 Kelvin. Determine the absolute enthalpy of the mixture on both mole basis and mass basis. Okay, gas stream, this one maksudnya dia punya product stream already. Bukan fuel dah, product. Okay, from the combustion, then here you have CO, CO2, and N2. Now, dia bagi mole fraction. CO is 0.1, CO2 is 0.2. Mole fraction. So N2, yes, remaining. So 1 minus everything, 0.7 lah. Kan? So 1 minus 0.1, 0.2. Now the condition dia bagi a gas stream at 1 atm. P 1 atm. T is 120, 1200 Kelvin. Gas stream, not the combustion chamber, the gas stream. Okay, so it asks you to find the enthalpy of the mixture. Enthalpy of mixture. So H mix, mixture of the gases. So we must find the total enthalpy of the mixtures. Nampak tak? Sekejap, saya besarkan. H mix, so total enthalpy of the mixtures. Okay, so that's why sini dia bagi the mixtures. Okay, mixtures. So mole fraction, sorry, the mole multiplied by the sensible heat, the heat produced, the enthalpy. This one is for CO. First part is for CO. Plus for CO2 plus N2. Okay, so we need to collect all the infos first before you can proceed for the calculation. Okay, follow me step by step. We know that this is the equation. We need to find the heat of formation for each component. Okay, always buat table so that easy to check. Okay, what are the components that you want to find? CO, CO2, and 2. The infos that you required, we need the HF. Okay, and then this one is heat of formation. This one is heat at that specific temperature, which is 1200. Okay, HT. Okay, yang ni dah different not the HF over here. This one different thing. So this one is H naught. H at STP. Okay. Now we need to use the table. Okay, saya buka table dulu. Okay, next class, it's better for you to print out the table. Easier. Okay, so we need the infos for HF. We find for HF first, heat of formation. So it is in table A26. Okay, this one. Found it, A26. Komponen yang kita perlu is CO. Okay, CO. So cari CO. Ni, jumpa. Okay. So ini adalah HF dia. Kilojoule per K mol. Okay, unit pun penting. So negative 110,530. Masukkan dalam table. Okay, next cari for CO2 and N2 also. CO2 negative 393. Okay, then N2 0. Okay. Okay, boleh. Now, nak cari HT, you need to use different table for each component. So first kita cari for CO. CO, H at 120 and H at 298. Okay, ini at 120K. So kita cari table for CO. CO. Moving upward. Okay, here. CO. A berapa? A21. 120 Kelvin. Okay, so ini dia punya enthalpy. Table A21 for CO. So at 1200, the enthalpy is positive, 37,095. Okay, so still at the same table, find enthalpy at 298. Okay, sini. Eight, 6, 6, 9. Okay, boleh. Next, find for CO2. Table A20. Okay, so cari 1200, which is this. Then find at 298. 9364. N2. Different table. A18, N2. At 1200. Okay, 36,777. 298. 8669. Similar to CO. Okay. N2 tadi table A 18. CO tadi table tadi CO2 A20. CO table A21, I think. No, A21. Okay. Boleh up to that? Now, after you have collected all the infos, all the values over here, plug in into the equation. Masukkan semua value. So the X over here refers to the mole fraction. So CO X CO is 0.1. XCO2 is 0.2. XN2 0.7. Okay, try calculate berapa you dapat for the H mix. Jawapan dalam the next slide tu is a bit different. So after substituting all the infos, a bit different because they refer different table. So try to plug in whether you can get this figure. Whether you can get the correct value. Dapat. Dapat ni. Okay. Okay, so that one is in kilojoule per kmol. The question one, both kilojoule kmol and kilojoule kg. mass basis, mole basis and mass basis. Okay, so for mass basis, kita kena divide by the mass, which involve the molecular weight of the mixtures. So 0.1, which is the CO, multiplied by the molecular weight of CO. Then this one is CO2. This one is molecular weight for CO2, and this one is N2. Molecular weight of N2. So this one we get the mixtures molecular weight. Okay, then we divide the total kilojoule kmol tadi, divide the molecular weight. Okay, kilojoule per kmol. Why kita divide the molecular weight? Because we know that it relates with the molecular weight. So cancel, you'll get kilojoule per kg. This one you can get for molecular weight. Boleh? Kilomole per kg. Ingat kalau kita nak cari mole, which is mole kan, you need the mole. What's the equation to find mole? Yes, correct. Mass over molecular weight kan. Mass, which is gram, molecular weight is mole per gram. So cancel out, kita akan dapat mole lah. Kmol equivalent to kg. Kalau you guna gram, then only mole lah. Gram mole. Okay. Okay. Okay, now we go for a steady flow system where energy in equals to energy out. Okay, energy in refers to everything enters the system. You have the Q, the work, and then this one is the enthalpy of the reactant. In here refers to, in equals to out. Okay, in here equals to the reactant. It involves the properties of the reactant. Out, properties of the product. Okay, reactants here inclusive the air, fuel plus the air. Product, whatever gas produced from your system. Okay, so now enthalpy over here is enthalpy of your reactant equals to the E out, energy out, enthalpy of your product. Okay, the total. Sorry. So in short, it's simplified to this equation. Q minus W. Okay, Q here means Q in minus Q out. W here is the summation in minus out. Equivalent to the H product minus reactant. Okay, product minus reactant. Okay, so we go for this example. This one, don't be confused. This one, reactant minus product. The difference is from the sign. Okay, Q out here means Q out from combustion is negative sign kan? Sebab dia exo. So when you, kalau ini, product minus reactant. You just follow product minus reactant. This one dia play around with the sign. Okay. Now we go for this example. Consider the complete combustion of methane. Complete combustion. Methane CH4 with theoretical air. Means no excess oxygen. Okay, first thing first, you need to generate the combustion equation. This is the first step. Because in assessment, midterm test or final, most of the time I will not give the combustion equation. You must generate on your own. Okay, why we need to generate the combustion equation? Because we want to know how many moles of the component. Okay, the A, how many moles of CO2 produced, H2O and N2. Okay. Now looking to the process, this is the reactant, the in, okay, in, out. So the combustion, enthalpy of product minus enthalpy of reactant. Okay, next step, I always suggest you to do the table. Okay, put in table form so that you can see clearly. I make it bigger. Okay, from the statement just now. Okay, sini it doesn't mention you any temperature or pressure kan. So if there is no statement, always assume at STP. Yeah, you can always assume at STP. Now, okay, 25 degrees C, 1 atm. And then here, sorry, here it also doesn't mention the H2O produced is liquid or vapor. If there is no statement at all, you can assume on your own. Okay, here it assumes water product is liquid. Why you need to assume either one of the phase? Because the H later on will be different for vapor and liquid. Okay, so we know that this is the equation. Heat of combustion, or Q. Okay, sorry. Heat of combustion, just remain the heat of combustion. Product minus reactant. Okay, product here is the methane and the air. Sorry, reactant, methane and air. Product CO2, H2O, and N2. Okay, then next step, find the infos of all components. List down all the components. Okay, we have here CO2, H2O, methane, and we also have N2. Okay, find out the infos first. This is HF. Okay, so do you need to find the H, the sensible heat? No, because tak ada perubahan suhu, kan? Okay, from the statement over here, it doesn't mention any changes of the temperature. So sensible heat when it involves temperature difference. Since T2 and T1 the same. Here, H0 is at T1. Okay, so here there's no sensible heat because at the same temperature. So we only consider the HF. HF of the component. Okay, so if only HF, find out in table A26. Okay, for both, for all components, go back to table A26. Okay. Yes, you can assume either one, liquid or vapor. If you assume vapor, then you just take the value for vapor. In this slide, it assumed as liquid. Okay, so here CO2, heat of formation. This one. Then water, liquid. So it assumed as liquid, so you just take as in liquid. 285. 285, 830. 830. Then methane, CH4. Yeah, CH4. Negative 74850. N2, 0. That's why in the table here, it doesn't mention N2. Okay, then from there, plug in into the equation. CO2, this is for CO2. HF, CO2. This one is, okay, product minus reactant. So CO2, H2O. N2 is not considered because HF 0. Okay, minus the reactant. This is the methane. Okay, how about this rest? The air. Why does it include the air over here? Huh? Reactant. Okay, this one is product. This part is product. This is product. CO2, H2O minus reactant. Reactant is methane and air. Air is O2 and N2. Why it doesn't include the O2 and N2? Same as N2 case just now. HF is 0. O2, HF is 0. Because the HF is 0. Then it doesn't involve any sensible heat. No temperature change. So by right, this one minus H4 minus the air would be 0 lah. O2 and 2. 0. And here I put out O2, HF is 0. So that's why there is no air considered in the reactant. Then from there, you calculate the heat of combustion produced, we'll get this figure, negative 890. Okay, this one in K-mole basis, mole basis. If you want to find in mass basis, if the question required in mass basis, then you need to divide by the molecular weight. Molecular weight of the fuel. Why not molecular weight of the product? Any idea? Why not? Why kg fuel per fuel? Because the energy produced is due to the fuel, because of the fuel. That the fuel supply combust, energy is because of the fuel supply. That's why divide by fuel, per kg fuel. So meaning that 1 kg of methane can produce this energy, this much of energy. Negative there means exo. It releases the heat. Okay, so kalau just now we assume water in liquid form, this much of energy produced. But if we assume water in vapor form, the HF used is different. So a bit different on the heat produced. The QC per kg fuel also a bit different. Okay. Okay, let's start there first. Digest first. Do you have any? If you have any question, then ask. Okay, Bennett.